All right. That's the first question. Now we'll go to the next question. Uh, who else want to do it? Pooja, you're here, right? See, Uma, we have binary search tree, which means it's quiz 2.
Yes, yes.
Okay.
So, what is the predecessor node? You should be able to read the question. I'll also take the options. Have more options. Make sure that we are checking everything. Fine. Go ahead, Pooja. It's your choice. Read the question first.
Consider the following binary search tree. The letters indicates the name of the nodes, not the values that are sorted.
Stored.
What is
That was
the
stored.
stored? Sorry.
Yeah, these are not the values, just the letters representing that node.
Okay. Then what is the producer node in terms of value of the node m?
Hmm. How do we find this?
No idea.
Okay. Does anyone want to try this? Anyone who knows this?
I just want to try the answer. I don't know that yet. So
I think Vikram was about to tell something. Wait, Uma, let's see. Vikram, you want to say? Vikram? I think you unmuted. Fine. Okay. Uma, go ahead.
So I don't know. I'm just trying. So the value means in a binary search tree,
Mm-hmm.
you should check with the parent, right? It should be
Correct.
greater.
What do you mean?
The parent should be greater than m, right? So we should
Right.
find the index of the parent.
Correct. So they are
Index.
asking predecessor. Okay. Predecessor. Okay. If you are writing this as a list, okay, this is a binary search tree. If you are writing this as a list, how will you write it? So first will come A.
B,
Wait.
C.
Is it A or H? H will be coming first, right? Like that is the smallest one. Right in the sorted order, ascending order. Uma.
Okay. I'm
This
getting
is going to be the middle value. Am I
Yeah.
right? So predecessor means the previous value. Okay. So what was the previous value for M? That is the question here. Okay. Now we need to write this in the sorted order. Okay. So I am just going to take a little bit extra time, but this can be done just looking at it. Okay. So, but still, to make sure everyone understands it, H. Okay. That is the smallest. What is the next smallest?
If it is sorted, then it will come D, right?
Correct. Go ahead. Next.
O,
O,
I, P.
I, P.
P.
Good.
Then B,
Then
J,
B
E,
for ball.
K. Yeah.
B, J,
J, E, K. It's kind
K.
of in order traversal, right?
Exactly. Right.
That is the pre-order. Sorry, that is the
Go
sorted
ahead.
one.
Go ahead. A. Then
L, F,
mm-hmm.
C, M, G, N.
G, N. Okay. So, Pooja, you need to write it like this in order. Okay.
Yes.
Now tell me what is the predecessor node for M?
It's C.
Very good. So hence the answer C. Got it?
Yes, yes.
Oh, it is not compared with G then, not is that kind of one. Okay.
Repeat.
So what is the question? So it is not G then, right?
No, it's not G. It is C. I'm sorry, C.
So we have, okay, we have to write it down in sorted order. Okay.
Correct. So predecessor. What comes before this? Nothing.
Okay.
Is that fine for all? Mahi, you got it?
No, but in the figure, it's a G is coming before M, no?
It looks like that. It looks like that.
Yeah.
It looks like that. But if you see the actual value of G is greater than M, right? Subramaniam, do you agree with that? Value of M is going to be greater than, G is greater than M.
Obviously, G is greater than M. That's right.
Exactly. And they're asking the value which is just before M, predecessor of M.
What makes that one is the value, is it?
Which one? Sorry.
What makes C become the predecessor? It's the value makes the predecessor as C.
Correct.
Okay, thank you.
Yeah, good. Any other people have any doubt here on this question? Fine. Pooja, okay with this?
Yes, yes, it's okay.
Yeah, nice. So we'll go to the next question. Since Pooja did not do that, you can also try to do this question. Okay, let's first explore these options, then we'll go. Go ahead, Pooja. Just read the question.
We want to support the operation next is smaller and next larger in a heap. Given a
Okay.
value v in the heap, next is smaller v give us the next smaller value of v in the heap,
Hmm?
and next larger v gives us the next larger value of v in the heap. Which of the
Okay.
following statements is true?
Correct. Okay. Hmm? You got the point, right? The question.
Yes,
Which of the question is like which of the following is true? That's all.
yes, yes,
Okay. So we have next smaller means it gives us the next smaller one. I mean, which is the previous one. The next larger means the next value. Okay. Go ahead.
yeah.
We have read the options.
In both minimum heap and maximum heap, both operation take order n times.
Okay. How? Why? Hmm. Any idea?
Once again, what operations?
The height.
Next smaller and next larger.
Oh,
So I'm just going to take some min heap. Yeah, this is min heap, right? Huh?
yeah, yeah.
Okay. So if I want to find the okay, in both operation takes, okay, fine. If I want to find the next biggest number for 6, this is a min heap. So that 7 can also be here, right? Ideally, it was 17 here. Huh?
But whatever wrote is also correct, right?
Sorry.
Whatever you
Yeah,
have
whatever I
written,
wrote is also correct. Whatever
yeah.
I wrote is also correct. So basically, you need to search the whole thing. That's the point here. Okay. Uh, am I right or wrong? Right, right.
Yeah, we don't know. In heap, traversal is kind of order of n, right?
Correct, correct. So we won't know where the 7 is getting stored. Like it can be here also. It can go towards the end, something like that. Can be anywhere, right?
Yeah, we don't even know if it's a 7, right? We just know we have a 6, and we have to find the next
Yeah.
next
Maybe we
smallest or
can have
next largest.
6.25 here. Maybe we
Hmm.
can have like 6.01 here. Who knows?
Yeah,
We have to search the entire. Still, it's a minimum heap. We have to search the entire heap to find out. Am I right, Uma? Got it?
Yeah.
Pooja,
Yes.
you have any doubt?
No, no.
All right. Subramanyam, you want to say something? Nikhil?
No, I'm
Mahi?
okay. I'm okay.
Yeah. Okay, great. Mahi, can you answer the next option? Are you here, Mahi? All right. Yeah, Mahi,
Uh,
come on, go ahead.
in both min heaps and max heap, both operation takes log n time.
Which is not the case, right?
Yeah, it's big of n times.
Hmm.
Yeah.
Hmm. You're
In
right.
a min heap, next smaller takes big of log n times, and the next larger takes big of n times. Whereas in the max heap, next smaller takes, it's wrong actually.
This is also wrong.
Yeah.
Both actually takes big O of n. That's what this. I think there's a single select option, right? So it's fine. So I think we are okay with this, right? This question should be okay. All right. So we are moving to the next question. All right. Here, Mahi, you can try to do this also. Read it.
Uh, Given a graph where all edges have positive weights, the shortest path produced by Dijkstra's and Boltzmann-Ford algorithm may be different, but path weight would be same. Okay, first statement is this: given a weighted graph where weights of all edges are unique, there is always a unique shortest path from a source to a destination. In such a
Okay.
graph.
So let's go one option at a time now. Let's explore one option at a time, one statement at a time. Okay. We are given a graph. All edges are positive weights. Fine. So if all are positive, we can use Dijkstra's, right?
Yeah.
And Dijkstra's doesn't allow edges to have negative weights, right? All right. So we have Bellman-Ford. What's the saying? The shortest path produced may be different, but path weight should be the same. What does this mean? Why is this true? Can anyone answer? Can anyone try to answer this? Okay. Fine. So what I feel is that um, let's have a graph, right? A, B, have C here. Then we have D, right?
Because Bellman would come back and update, right? Rather than Dijkstra.
Correct. That's the point here, right?
For me, second also looks correct. I don't know.
Fine. First, let's talk about the first option, Uma. So if we have, in 20, right, have 5 here, 5. I don't know. Like I'm just taking some options. Okay, I'm randomly taking. I'm not sure. So how do we explain this? Shiva, you have any option to explain? Afnan, you want to say how to explain this option? You have any idea? I really understand that, but just to explain this.
Yeah. So Bellman-Ford you only use. I mean, it's you can use Bellman-Ford for negative weights, right?
Yeah,
So
negative weights also.
if it is only positive, it will work very similar to Dexter's.
Correct. But they are saying that path may differ. Uh,
Yeah,
but
because they haven't said if there are unique paths, unique edges or not, right? So there can be many edges with the same weights, and Bellman-Ford might pick a different edge, and Dijkstra's will pick a different edge, right?
mhm. It's okay for me. How do
I
we
think
explain to
that's
others?
what. Yeah.
Yeah. What about others? Did you guys understand this, or what should I tell?
When the
Uma?
path weights are same, thinking, okay.
Okay.
Will it not give the same output? Both Dijkstra and.
Not necessarily, right?
Okay.
How do I explain this in a graphical way?
It's okay. Fine. If you're saying that same weights, right?
Yeah. Okay, I think I'm getting some idea. 2, 3, and we have something like 5. Okay, and this we can give some like 15. Okay, so if we take the Dijkstra's algorithm, Uma, so Dijkstra's algorithm will A to C, right? Then C to D,
C to D.
right? So this is, I mean, just like how Steve and I told. So at the second minute you will reach C. Okay, starting at A. Second minute you will reach C. Then at the fifth minute you will reach D, right? So and then at the 15th minute you will reach B. So this is the Dijkstra's algorithm. But in case of what's that other one?
Bellman-Ford, right? Yeah.
Bellman-Ford. Yeah, that's correct. See, in Dijkstra's algorithm, you might have got this path. So the algorithm is just single source shortest path, right? The question is like A to D. How fast can you reach, right? Dijkstra's may give us ACD, but Bellman-Ford can simply tell that you can directly reach like this, A to D. Uma,
Okay.
following?
Yeah.
Yeah, it updates. So
Hmm?
in Bellman-Ford, we are updating the we're taking the next edge so we're taking, including one edge. If I take one extra edge, what is the estimated time I can reach there, right? So
Yeah.
in this case, you're actually, so the first, if there's a direct edge, you just update it to 5, and then the later edge, if it is later in what is that, in between edge, right? If that is updating it better, then you update it again. Like, because if there was a negative edge weight, then it can reduce. Or even if the edges are smaller, like 2, 1, 1 actually takes you to D instead of 5.
Yeah.
You would have changed the path, right?
Correct. Uma, okay, but we can clearly say that path weight should be the same, right? I mean, the shortest path is going, weight should be the same.
Yeah.
That's okay, right? You agree with that, right?
Yeah.
Mahi, okay, Pooja?
Yes, yes.
Subramanya, Mahi, are you okay?
Can we revisit the statement and check that one? The extras and women 4, the path is same, but the weights are different, is it?
No, the other way around.
The path is different and the weights are same.
Yeah, the total shortest path between one source vertex and the destination vertex is the same, right? So this is the shortest path. You know that you have to do at least 15 amount. You have to wait at least 15 seconds for the file to reach D, right? You're just saying this is not unique. That Bellman-Ford might create a different path to B rather than taking from A to B. It might go from A to say a second vertex, and then a third vertex, and then to D, right?
Mm-hmm. But the weights are smaller than that one, no?
Yeah. The shortest path, it's going to be always the same in both the cases.
Yeah.
I mean, path in the sense, the path weight. You mean the shortest distance?
The weight is the distance, is it?
Yeah, exactly. Weight is the distance. The sum of the weight is going to be the same in both the cases. That's what they are saying.
Okay. So
path weight is nothing but the sum of the weight.
All right. So 2 plus 3 plus 10 and 15 both are same. That's what you are trying to tell.
Correct. And also see 5 plus 10 also is the same.
So telling maybe A to B, Dijkstra will choose A to B that 15, and Bellman-Ford might choose A to D, D to B. Is that what you're telling?
Yeah, maybe.
Yeah.
Okay.
That's the point. Okay, fine. So actually, that's the case.
Just for the sake of solving the problem, we fix the values. It's a dummy values now.
Yeah. An example.
Oh, that's a bit difficult. I don't know how to reach out to that thinking. All right.
Okay. That is the case. Do we have an algorithm which will give us the path already? And do we have the code which already gives us the path, or just the weight? What do we have?
No. I think he's trying to say during the exam, how do I think of answering this question, right? That's what he's trying to ask.
Yeah. That's a point.
Yeah. So
Go ahead.
I think Dijkstra's and Bellman-Ford both get the shortest path, right? Shortest path given a route, given a source vertex and given a destination vertex. I mean, it doesn't have to give destination vertex because it computes for everything. But given the source vertex and a destination vertex, it gives us the shortest path, right? Both of them give the shortest path. Bellman-Ford is just an adaptation to Dijkstra's in a way that it can not adaptation in the sense that it implements in the exact same way. What it does, it takes the intermediate node, which is connected to so I to j, j to k, right? It takes addition of that and updates the distance. Instead of updating after reaching j and then exploring j and then visiting k, right? Do you remember the Bellman-Ford algorithm?
Yeah. No, lost it. So,
okay. Yeah.
I'll revisit it, right?
Yeah, maybe we should revisit it. But yeah, the main goal is that what we do in Dijkstra's is we explore a vertex completely. The first, like just the direct edges from that vertex, right? And after we explore a vertex, we go to the nearest one which has been explored and explore that only one edge at a time, right? But in Bellman-Ford, what we're doing is we take intermediate edges and we think, okay, if I used one extra edge to reach J, if I used I to K and K to J, sorry, we use it the other way, right? I to J and J to K. I might be confusing. Like, yeah, if you want to reach a vertex J, and if I use an intermediate edge, right?
Okay.
I'll update it directly from there instead of exploring I completely and then exploring K single by single. That's the Bellman-Ford algorithm.
Understood.
Yeah. So yeah, it might be confusing if I tell it like this, but maybe if you go through the code, I think the code is very simple. It's just a 3 for loops, I guess. I think it's very simple. And if you see the, I think illustration.
Is there any keyword to have first pass elimination in these questions?
Maybe that's difficult. Let's look at the question and try to figure out something.
Yeah, is there any keyword? Because it's more sounds like shooting in the dark now.
Yeah. Yeah.
Food, we update it again and again, right?
Yeah, exactly.
We
Yeah.
revisit, but in Dijkstra, we will never revisit the explored ones. But in
True.
Bellman Ford, so I thought if only negative weights, it will be different from Dijkstra. But in this question, it is given, though it is positive, still it is giving you. That is what tricky.
Yeah, that's the case of equal weights, right? If you're able to reach D in two ways, one way which is taking 15 seconds and the other way is also taking 15 seconds,
Yeah.
Bellman-Ford will take the most updated, most recent one, whereas Dijkstra should have taken the first one because it's a greedy strategy.
Yeah.
Exactly.
So
Right?
the path
That's
maybe.
that's the main crux of this statement.
Yes.
Can we make a conclusive statement that Bellman-Ford always gives an optimal path comparing Dijkstra?
No, both are going to give us optimal.
Optimal in the sense of path weight,
Between,
right? Because it's going to be equal. Yeah.
okay, here in this case it's equal. That's the way we chose the weight.
Yeah. The only difference is that if you are able to reach using three intermediate edges, right?
Okay.
You were able to reach with one intermediate edge, okay. But if you're able to reach also with three intermediate edges and the path weight is the same even with that, Bellman-Ford will store that value because it updates every time.
Okay.
Yeah.
Got it.
Good. So let's move to the next option. Mahi, continue. Mahi? All right. Go ahead.
Given a weighted graph where weights of all edges are unique, there is always a unique shortest path from a source to destination in such a graph.
Mm-hmm. Is this true or false? Why does this sound like true? And the answer is false. It sounds like true, right? Uma?
I also felt the same. Maybe the weights are not positive.
All right. So they are saying that,
Yes.
okay, there is always a unique shortest path from source to destination in such a graph when the weights of all edges are unique. Okay. How do we generate a counter example for this?
I thought that is true, right? When the weights are unique, there should be only one shortest path. Okay,
Correct.
Afnan.
You guys are missing one aspect of it. Like
I
what
got it.
makes what
Yeah.
makes shortest path not always unique. There are other.
Something like this. Afran, please go ahead.
Yeah, so I think the second statement is mostly a continuation of the previous
Yeah.
discussion that we had. So in the previous example itself, we had something like equal weight, from source to destination, but we are having different paths.
Yeah.
So that is like a counterexample for this, right?
Exactly. That's right. That's
Because in
perfect.
this case also, in this case also you can see that, I mean, talking only about the edges, we have unique numbers there. So we have
Yes.
2, 3 and 5. So that
Mhm.
accounts for the unique thing. But then if you talk about the combination, as Nikhil is saying also, so then it will be 5 and you may get a different path, and that
Correct.
also will
So
qualify as a shortest path.
so A to C, there are the shortest path is like there are two different paths.
Right.
Right? Uma, got it?
Yeah, got it.
Now this makes perfect sense. Mahi, okay? Pooja, Mahi?
No,
Okay,
Yeah,
tell
yeah.
me.
Okay.
Mahi,
No
tell.
problem.
I didn't get.
Okay, read the question again. There is always a unique shortest path from source to destination if given that if you have all the edges are unique. See, all the edges are having unique weight here, right, Mahi?
Yeah, yeah.
And how many shortest path do you have to reach from A to C?
2.
So does this is an opposite, right? They are saying that there is a unique path.
Okay, yeah, yeah. Okay, got it.
Gokul, are we having a unique weight for all the paths?
Aren't we? Unique weight for all the edges. It's given like
Yeah,
weights of
unique
all
weight.
the edges.
Yeah, 2, 3, 5 is the edges we assigned it to the edges now.
Correct.
And is it unique?
Aren't it? Isn't it unique? 2, 3, and 5.
Okay, it's not equal, huh? So unique. Okay,
Correct.
okay. I should not have a repetition of any of these edges, is it?
Exactly. Repetition of any of the
Okay.
weight for the edges. You're right. Okay, is that clear?
Yeah, I'm done. Thank you.
That was an interesting question. Seems like the first batch had the toughest question, right?
Always first batch.
I'll agree.
Hey, I won't agree. I won't agree for that. At least for PDSA, you can say. Okay, fine. What do we have here? Hey, this looks like something we have already seen. Are we doing the same question? Yeah. Oh no, wait. Set one.
No, I think you went to.
Okay, why do I have everything open? Let me just close these. That's why it's confusing. When we have it. Yeah, it's continuing. Sure, we also have the same.
Yeah, we had the same question, maybe.
They see they are repeating the questions after every term. So, which of the following order will be printed by the given code snippet? I
Slightly
think you
different.
guys.
Today it was numbers, I think so, right?
No, I don't think so.
Oh, it's the same thing? Okay.
Yeah, so that they are asking which is going to what is the path? How is it going to go? We saw it, right? First the leftmost one, then the rightmost one. I mean, first you the left edge, then the right edge, then you go to the parent. When both are completed, then you print the parent. Do you guys remember that?
Yeah. Got it actually. This
Mahi, Pooja,
Yes.
Yeah.
like, do you guys know this question already, or is anyone having doubt on this? If anyone want to discuss this, we will discuss.
Yeah, explain this, please.
All right, cool. So, what is happening? So they are saying that I'll finish this up fast. Which of the following order will be printed by the code snippet? All right. So they are calling the traversal function for the root. See, traversal of root. That is what they are calling, right?
Yeah.
Okay. And the root, they are saying that root refers to the node A. Okay. For the node A, they are calling the traversal function. So I'm going to write it as traversal of A. So what is it doing? If t is not equal to none, is t not equal to none? No, right? It's not none, right?
Yeah. It's a
So correct. So we do two things. So traversal of t dot left. What is t dot left? B, right?
B.
And then t dot right, it is C.
C.
First you complete t dot B, then you go to that. Okay. So for t
Okay.
dot B, again you're calling the traversal, and since B is not none, you're gonna do this. So t of D, then you do t of E.
E.
Okay. So now you explore the left hand side first. Okay. So t of D, your what is traversal of t of D? It is none, right?
Yeah. It's none.
What about the right? Right also none, right?
Yeah.
Okay, so if both traversal of t is none, and left is run and right is run, so you got the point. Now it is going to print the value, t dot value. What is the value?
E.
D. It is going to print D. Followed?
Yeah.
Yeah.
Okay. After that, what are you going to? I mean, now that you have explored this t of D. Okay, I'm just taking a different color. So now that you have explored t of D, that means the left part of traversal of B is done. Correct?
Yeah.
Okay. So now, so when you are doing that T of B, right? So first you do the left part. Now that left part is done, so you need to go to the this line, correct? Fourth line.
Right part.
Very good, right part. So you're coming to the traversal of E.
E.
And for traversal of E, you have two things. I mean, you're supposed to do left and right. So on the left, you have something which is T of H. On the right, you have empty. You don't have anything.
None.
Okay. So since you have something on the left, you go and do the traversal of this. None, none. So which means what will get printed?
H.
Very good. H will get printed, right? So after H,
E.
no, you need to see, yeah, that's correct. But you need to see the right hand side. There is nothing. So that's why you're printing E, correct?
Yeah.
Yeah.
Good. So now that you have explored left hand side of B and the right hand side of B, so now since these two lines are done for the B, so you can right away print the value of B, right?
E.
So when you followed,
Yeah.
great. Okay. Now that this left hand side is covered, so now coming back to A. Now can you tell me what will happen?
Traversal of C.
Yeah,
Left and right.
correct.
Left
Left and right.
G. Then
Hmm.
again left I.
Okay. So traversal I will be printed. Good. Then we don't have anything on the right, so we can print
No.
F.
F.
Very good.
Then
So we don't have
G.
anything on, yeah. Then G,
Then
then
C.
comes C, then
Then
comes A,
A.
right? So this is how the order is. Let's just confirm that. Um, okay, see, D H E B I F G C A.
Yes.
We got the correct answer. Yeah, Subramaniam,
Okay.
okay?
Yes.
Yeah, and this we also discussed. If you have having doubt, like we discussed this very detail yesterday, we can go ahead, right? Mahi, okay? Everyone else is okay, fine with this?
Yeah. It's all right.
Great, nice. So we'll go to the next question. Subramaniam, can you take this question? Let's take this question. Yeah.
Uh, which, which of the following statements is true about complexity of the given function?
Correct.
N is the number of nodes.
See, so they are this question. I mean, there are two sub questions, third and fourth. All right. I mean, sorry, 6 and 7 are the sub questions. So they are asking for the complexity for the previous one.
Yes.
Mm-hmm.
So the following statement is true about ON. What are the options? O and log n. Whether the tree is balanced or unbalanced.
Mm-hmm.
O n if the tree is balanced. O and log
Yeah.
n otherwise. O n whether the tree is balanced or unbalanced. O and log n.
Go ahead. So this traversal function, they are saying that how
Same
much
question.
is the,
Same question, is it?
yeah, same.
So we got to really build the answer based on the heights, is it?
Based on the heights. Okay. So what do you mean? What do you mean?
N is equal to 1, 2, 3, 4. Is that right? In the
I'm
tree,
not.
in the
Yes.
in the tree, the height of the tree is 4.
Correct.
N is equal to 4.
No. The question is, n is the number of nodes. See, n is the number of nodes.
N is the number of nodes. Okay.
Correct. So in this case, n is equal to it's 9.
9. 3, 6, 9. Okay.
Mm-hmm.
Okay.
See, what is this traversal function doing? Can you tell me what is this traversal function has done? It has printed all the nodes, right? In some different order, in some order, it has
Yes.
printed.
All the nodes,
Right.
no node is missing.
Yeah, I mean, I forgot to print A. Okay.
Okay.
Mm-hmm.
But
So yeah,
the
go ahead.
order is different, is it?
Yeah, only the order is different.
Okay.
Okay, but if you can look at this, so it is going and exploring all the nodes starting at a given node, right? When does it come to an end? When it explores all the nodes,
Yes.
right? So which means what?
N.
Very good. Which means the complexity of n.
Yes.
Is there any other explanation for this? Anyone else want to explain this much deeper? All right. Okay. Again, we have explored that in the yesterday's question itself. Yeah, I think this is like, why are they high in the same questions and all the time? Fine. I know that taking questions are harder.
Yeah,
Shivani,
first-hand experience.
are you preparing questions this term? Can
I
we have
can't
some
say,
questions?
but I'm not preparing any exam questions. So don't worry.
Okay.
Actually, I think exam questions are prepared by professors. I guess I don't even think instructors know what questions come.
Wow, that's nice. Really nice.
Yeah.
Well, ideally, they have less time to take new questions, which I can clearly see from here. Right. So let's do. Who want to do the Afnan? Come on, go ahead. Why are you silent? Are you here?
Yeah. Okay, just a second.
Yeah. Go ahead.
So I think we also have a session, at 8 today.
Yes,
That
yes.
also is a revision session for
Yeah,
PDS.
yeah.
Anyway, so yeah. So this question I think I also explained yesterday also, I think. But anyway,
Same.
yeah.
Yeah, yeah.
So it is asking about the number of elements. No, consider a binary search tree of height h. Then which of the following statements is are true? Okay.
Hmm?
So the number of elements in the tree is at most h. So elements, I believe it is talking about the vertices that we have, right? So
Yeah.
elements is basically referring to vertices. So h is the
Mhm.
height, right? And it is definitely not equal to the number of elements that we have. So the first option is definitely wrong.
How?
And then we move.
Why?
See, because number of elements is the vertices, right? So then height, if we have height, then it is not necessarily equal to. Okay, in this case, it might be, but then yeah, you're not considering whether it's a perfect binary tree or not. All
Exactly.
right. Okay.
Why is
Okay.
this option wrong?
I mean, perhaps it is not always the case. That is why they are, because this I think is a special case that you have drawn. No, I don't see any other reason.
At most H, right? Like maximum could reach a H. Shivanai,
It
you have any
it
suggestions?
could be more than that also, no? Because I mean, most of the time it will be more than what we have as the
Yeah.
height,
Ah,
right?
yeah.
So it's
Yeah.
saying it's at most 4, but we can have much more elements than 4, right?
Mm,
What?
So, okay, number of elements is equal to 2 power h minus 1, right? At most.
right.
Huh.
So how can it be? So it can't be at most h, right? It has to be.
Okay,
Yeah.
okay. So H is the height. So given that, if let's say that if you are given a binary tree, right? So this is a binary tree, right?
Yeah.
Okay, and the height is like 1, 2, and 3 is the height of this binary tree, right? So
Right.
and we can say that it's not the case. So at least H, I believe, the number of elements in the tree is it at least H? If it was
Yeah.
at least, then it will be true, right?
That the second
Shrivan?
option is there, no? B is correct.
Yeah.
Exactly. We have it here.
Nikhil
Nice.
also put it in the chat. Yeah.
Guys, are you able to follow this? Like Uma, Mahi, Pooja?
How do you say at
Yeah,
least?
it's okay.
See, uh,
At least for a
how do we say at least?
Yeah, the example you took, right? That's the
2, 3, 4.
the
Okay.
only.
Yeah. For that right hand side picture, it is at least.
Both B and D cannot be to same. Both B and D cannot be right at the same time, no?
Yeah, at least and at most cannot be the same.
So they are not. Is it not conflicting? We are
No,
still
it's
like
saying at least h and at most 2 power h minus 1, right? So they're
Hmm.
giving a lower limit and an upper limit. Lower limit is h, right? So if you have
Mhm.
a height h, the lower limit number of elements you can have is if you have a one skewed, completely skewed
Linear. Yeah,
linear, yeah,
linear graph,
binary,
you can say.
yeah, yeah. So it will at least be 4 because in this case it will be completely linear. At least be 4, which is
Mhm.
equal to the height. Or if it is a full binary tree or a perfect binary tree, right? Then it's a it's 2 power h minus 1. Yeah. So that's the maximum.
Uma?
Yeah, got it.
Good.
But that will that work for the given tree? Now you're given an example of a single pass 1, 2, 3, 4. That's
Yes.
H is 4.
Mm-hmm.
H is 4. H is 4. And the height is also okay. Then 2 power h minus 1 is 7, is it?
Yeah, here in this case 2 power h minus 1, that is 7. 2 power 4 minus 1, which is equal to 7. See how many nodes do you have? 1, 2, 3, 4, 5, 6, 7.
No, no, I'm not talking about that. I am talking about the other one. 1, 2, 3,
Uh,
4. Right one.
okay, right one. Okay.
Mm.
What are you saying?
So that does not have 7 nodes. That's only having 4 nodes.
Yeah,
Hey, hey,
at
hey.
most can have. So if you have a binary tree,
Mm.
so do you agree that the right hand side, the blue, the one written in blue,
Mm.
do you agree that it's a binary tree?
Why not? Yeah.
It
That's
is,
correct.
right? So this is a type of binary tree which is kind of linear, right? It looks like a linked list, right? This is the worst case scenario. It's not balanced at all. Like that's what you would say, right?
Yeah. But,
In that case,
but the rule is not holding good there, is it?
it's not about a rule. The rule is saying, see, if I have height is equal to 4, the maximum number of elements that a binary tree of height 4 can have 7. 2
Mm.
power h minus 1, which is 7,
No,
right?
it's not 7. It is not 7. 2 power 3 minus 1 is 7. Shriyane. It's
Ah,
15.
Sorry.
oh yeah, it's 15. Right.
Yeah, okay. Okay, wait. Subramanyam, let's say like h equal to 3. Okay.
Yeah.
Okay. For this, if I want to draw a binary tree, what is the least one that I can draw? It's a straight one,
Straight one,
right?
yes. Mm.
Okay. So if I remove one of the element, okay, will this become h equal to 3? No, it will become h equal to 2, right?
2, yes.
Yeah. So at least I need 3 elements, right? Yes or no? At least I need 3 elements in order to have a height of 3. Yes or no?
Yes.
If I remove anything, then it is gone.
Height
Right.
reduces to, yes.
Correct. Okay. Now see something. I'm going to draw 0.5 here. Is this a binary tree of height 3?
3,
Yes or
yes.
no?
Yes, yes.
Okay. See, now I'm going to draw one more thing. 0.25. Is this binary tree still?
Yes.
Still it's a height 3, right? Now
Yes.
0.75. Still it's
Yeah.
the same.
Mm.
Okay. Now I'm going to put 2.5 on this.
Mm.
Not 2.5, it's 1.5. Right? Should be 1.5. Left hand side should be smaller.
All right.
See, this is still a binary tree of height h. So now this is the maximum. If can I put one more over here?
No,
Will the height be 3?
the
No,
height will
right?
change. Height will change.
Exactly. Maximum how many I can have?
7.
Very good. Which is 2 power h minus 1.
Oh, that's what really you meant to say here. Okay, I got it.
Yes.
Thank
Okay. At least 3 you should have. At most 7 you can. At most 2 power h minus 1.
you. Okay, the simple linear one is the minimal, and the 7 more
Complete
one
one.
is the maximum. Okay, I got
Yep.
it. Right. Thank you.
Cool. So that's all about the first 4 options or first 5 options, I believe. Number of elements in the tree. That's all. Nothing else is there. Last option. I mean, can you do this, Afnan? You are doing this.
Yeah, okay. So in a binary search tree, if the number of nodes with 0 child nodes are n0 and the number of nodes with 2 child nodes are n2, then n0 is equal to n2 plus 1 is always true. Okay,
What was-
what is that saying actually? So we'll have to think
Are we
about it.
considering this in continuation? This in this statement, the number of elements in the tree is at most 2 per h, which is wrong. Oh, I think what is this? Is this a different question or different option?
No, I think it's part of the
Okay,
same
that's F
question.
option. No, this is a F option. Same
Okay,
question, but the option number is F. I thought
F.
you know.
All right. So what it is saying basically?
Yeah, this is the option. In a binary search tree, is the number of nodes with 0 child nodes. So we can see that number of nodes here in this case is 4, right? The
Right.
last one, the lower one. Okay,
Mm,
or n0, and the number of nodes with 2 child nodes are n2. So
okay.
in this case it is 3, right?
Right.
N2 equal to 3 and n0 equal to 4. Okay, So then
That holds
n0,
true. Yeah.
yeah, then
P
n0
plus 1 is
equal to n2 plus 1. That's correct. That holds true, right? That always is true.
correct, correct.
Uma,
Because
did you understand this?
it is related to the fact that before moving on to the next level, we kind of
Yeah,
assure that the previous level is filled in, but that is only in the case of,
completely filled.
yeah.
But what if in this case, so you have three and zero,
Mhm.
right? So
Correct.
how many? No, not three. It's actually five.
No, 5. You have to add
Yeah.
below one also, right?
Yes, we have to calculate these. So
5.
we have five. Okay, how many completely filled are there? So one, two,
4.
three, four,
4.
four. Yeah, which
4
is
plus
still
2.
correct.
Correct. Yeah.
That is holding. Yeah. Okay. Okay.
Yeah. So I'll just try one more, Max. Is everyone following this? Subramaniam, are you following?
Yes.
All right. So if I just put one more, how many children? One, two, three, four, five, six. We have h naught equal to 6. All right. So 1, 2, 3, 4, 5. We have two child nodes as 5. So which is still holding. This is always true.
Okay. All
Hope.
right.
Yeah. This is interesting. Uma, got it?
Yeah, got it. Yeah.
Any doubts? Mahi Puja? What is your doubt?
No doubts. It's
Got
okay.
it.
Okay. If you're clear, we can move ahead. Fine. So what is this about? Okay. Who wanna do this question? Uma, go ahead.
Consider the min heap 10, 25, 45, 35, 38, 70, 54, 43, 39 built by repeatedly inserting values into an empty heap. Which of the following would not have been the last element inserted into this heap?
Hmm.
Actually, this wasn't disclosed, but I couldn't understand this.
Okay. We'll try to understand
Every,
this. So
yeah,
they are saying
every
that this is a
element,
min heap, right? So shall
yeah,
we just draw this first?
yeah, 25, 45, 35, 38, 70, 54, 43, 39.
39.
Yeah.
Okay.
Which of the following
So
in the last element? So we have to
do you
trace
think
that actually.
correct? Correct.
Delete it 10.
They're saying that if we had inserted 25 at the last,
But every element will be inserted the last only initially, right? That is my
yeah,
doubt. How
yeah,
can
yeah.
this could not
The
have
thing
been
is,
the
yeah. For example, um, let's say 25 was not there. Okay, if 25 was not there, how do you think he would have been looked like? It's a min heap, right? So the next minimum most value in this would have been at the top, right?
yeah.
Okay, and that 35, like since that has gone there, mm, any suggestions on how to do this?
Yeah, yeah, sure. Okay. So,
We're almost there,
yeah,
but
yeah, yeah. Okay. So we this actually is because of the property of in a heap. Where would you insert? Right, you would insert on the last level on the freest side. Right, you wouldn't insert anywhere else. You would insert over there. Right, that's the spot wherever he's marked it. That's where you would insert. Right. So that 39 was bubbled up. Like if either 39 was inserted, right, or whatever was inserted there was compared with 39 as a parent and it got bubbled down to the last leaf. So either it was 35, 39, or 25. Is that right?
repeat
Or
35.
10.
Repeat,
See,
repeat.
what I'm saying
Ha.
is
Okay, 35, 38, 25, 10.
no, not 38. So 39. So okay, imagine there's no 39. Remove the
Ah,
39.
okay.
Remove
Mm-hmm.
the 39. Let's remove the 39. Let's keep a dummy value. Let's insert something now, right? At this point, you're inserting something. Say it's X, right? Just say X, right? Just say X. Now, the only thing you will compare X with is what? 35 first?
Yeah.
Yep.
Then 25, then 10, right? Yeah.
Yeah. Either it will get swapped with 35 or it'll stay at the last leaf, or it'll get swapped with 35 and 25, or it'll stay at where 35 is. or it'll get swapped to 20, 35, 25, and 10. Right? It will happen like that, right? That's the path, only path it can take. So that's why 38 it can never 38 could have never been the element. So it's never, not in the path. So everything else is in the path. 25 is in the path, 35 is in the path, 39 is in the path. 39 we deleted, but yeah, it's supposed to be there. If you want to explain this better, you can, maybe.
Now I got the idea.
Yeah, cool.
So this is how it would have looked like, right? If we hadn't inserted, 25. This is how it would have looked like. Okay, I'll tell you why. So Uma, if you are inserting 25 here, okay.
So
Uma,
the question, I'll just understand the question. The question is, in this heap inserting value, is that the correct? Because I thought initially the question says inserting these elements, I thought. Then the 38 would have been in the last value and we would have compared, I thought. In this existing heap, we are inserting, when inserting new values, is that so?
No.
Then
So
only
they're just asking us, see, which of the, okay, we have a min heap from 10, 25 in that list, right?
Yeah.
Out of that list, right, what could have been the value? What could have been the last inserted value is the question, right? Let's forget the negation, right? Negation is could not have been, but what could have been the last value that was inserted, right? So he's saying, imagine until now this was your heap, right? And he's saying try to insert 25 because when you insert 25, that's when you compare the most, right? That's why it's only about the position because you're inserting at that second node to the right of 39. You can only compare in that path.
Correct. So Uma, if you're inserting 25 here, what will happen? 25 will go up and 39 will come down, right?
Yeah.
Okay. So 25 is here and 39 is over here, right? Now 25, 35. So we interchange these two, right?
Yeah.
25 and 35. So now does this look? These both look similar, right?
Yeah.
So if you have inserted 25, it would have gone over this path.
Yeah.
Right. So let's say now if I'm going to insert some lower value, say let's say like 22. At this point, if I insert 22, okay. So what would happen? It will compare
To the
here.
left. The
Yeah.
left of 38.
No. After this. Yeah. So the order you need to check is you just need to check these.
Yeah.
Okay. These are the things. Either if it is 28 or 22 or 38 or 25, this line will be changed. So similarly, I think that is what is happening here. So anything on this line could have inserted the latest if you're inserting at this position.
Okay.
Am I right, Stephen? Am I making sense here?
Yeah, that's the perfect answer. Right. Only if you're inserting there, only the elements which are parent to that or in that path could have been inserted. Nothing else could have been inserted.
Correct.
10 could have been inserted, 25 could have been inserted, 35 could have been inserted, or 39 could have been inserted.
Correct. Because if you're inserting something, that value cannot go and sit over here. Uma?
Yeah, got it. But when we insert 38, we are at that last, that is the last element, right?
Why? How?
Okay, let's try with let's try to insert 38, right? So say we have only till 43, right?
Yeah.
Right, we are till 43.
Gokul, like after 70, we are inserting 38, right? So at that point, 38 is inserted last, right? That somehow that is my doubt.
After 70, we are inserting 38.
Why? Actually, I don't understand.
Okay.
How are you saying that, Uma?
Okay. Empty heap.
Yeah, empty heap. Heap, you are filling it like this only, right? From left to right.
Yeah, okay, got it. Yeah.
Sorry?
Okay, I think he's on a different call.
Yeah. Mahi, Pooja? That's fine. Mahi and Pooja?
Yes, it's clear.
No, tell me how and why. Let it be clear, but I'm not going to let you guys.
So, Gokul, after 45, 35, we are inserting 38, right?
After 45, 35, we are inserting 38. Correct.
So, is it not the last element at that point?
Correct. Yes, you're right. Yeah, Uma. Ad- See, if the min heap was like 10, 25,
Okay,
45,
the last element. Okay.
okay, 35, and then 38. So then this is the last element. This is not just the last element. It could have been 25 also could have been the last element. All right. Or 10 could have been the last element.
Okay.
See, let's say that we are not inserting here. Let's say 25 is coming here. Okay. So if you are inserting like that, so let's see if you are getting a heap like this. Shall we check that? Will we get like that? I'm just trying. 10,
No, don't keep
45.
10 on top. Keep, okay, yeah. 10, 45, 35.
No, 35 is going on the right hand side though. So which means it's not the case, right?
Yeah.
38, which means 45 will go down and 38 will go up.
Yeah, that example won't hold because it's changing the location for the previous ones, right?
Correct,
So
correct.
if it was repeatedly built till now, you should not try to build it ascending wise, right? So let's say,
So we'll try to build from the start, Gokul, so that will be easy. So let's build 10 and 25 first.
Okay.
So we'll switch it, right? Because it is a okay.
no,
It's
no,
a min.
min heap, right?
Yeah, so we
Min
don't.
heap.
And now 45.
Okay.
Then we go for 35, right?
Sure.
Now it's a min heap. Okay, now it's
Yeah,
also
it's given as a min heap itself. Yeah.
okay. So now 38. So okay,
38.
yeah, 70. So that's why it is not coming as a last element. Okay.
No,
Yeah.
no, yeah, we can't, we shouldn't do like this actually, right?
Yeah, that's the thing. We can't build it up. So they've given us a min heap already, but they would have inserted in a different way, right? They could have
Yeah.
inserted in a different way.
Hmm.
So
And
let's
ended
say
up in
after 10, 25, 45, let's make sure the top triangle is correct. Then after that, instead of okay, 10, 25, 45, if I do that, then okay, the top triangle is correct. Okay, no, 10, 35, 25, 35, 45, and then do 25.
Hmm.
In this case, like it could have been inserted in this way also, right? That's what I'm saying. Like this would have still
Yeah,
given
yeah.
the same heap as below because the
Mhm.
25 and 35 would have swapped.
Yeah.
Yeah.
Okay. And there is also another way. I think we can trace back, right? Deleting 10 kind of thing. Can we do that? So that we'll get each. It will take time to understand. We'll get the previous stage, right?
Mm-hmm.
That's right.
Tracing back, so that we will know the heap structure at that point when we inserting 38 or something. What will happen?
So,
The thing is, they haven't given us in what order they're inserting it all, right? How will you trace
yeah,
that?
Okay. Yeah.
Uma, let's okay, instead of doing that, okay, let's say I want to insert some value here. Okay, so just like how he told. So let's say I'm going to insert the value 5.
Okay.
Okay, if I'm inserting the value 5, so where will 5 go? It will go to the top,
Yeah.
right? In what order it will go? It will from here. It will exchange with these
Yeah.
two, right? So it will again interchange these two. It will again interchange with this, and then 5 will go and sit at the top,
Yeah.
right? So you will have 10 here, and then 25 here, and then 38 here. You followed what is happening here?
Yeah. Here I got it. But how do you say that?
Okay.
Yeah, at the same spot, instead of so if 5 was not inserted there,
Hmm.
right?
And
And
yeah, 15.
wait, I don't want to explain it. I want to say, mm,
My
Yeah,
only
Uma.
thing is, Gokul, yeah, how do you say that 38 would not have been in the path? That is my question.
Okay, for this question, because 39 is here. Let's say that, I mean, this is the last, and not just 39, any element.
Yeah.
Okay, be it any element, be it like 25 or 40, whatever it is.
Okay.
Okay, so any element which is getting inserted at this position
Okay.
would
That.
have traveled up on this path only.
Okay. Okay. That's what we are. That last element position we are considering. Then we are saying that 38 could not have been there, right?
Correct.
yeah,
So
yeah,
yeah,
exactly.
whatever element you are sitting, if it
Okay.
is lower than 35, it would have gone and settled
Yeah. Yeah.
on
Got
this
it.
line. It would
Clear.
not have a.
Just that position matters. Yeah. Got it. Gokul. Yeah. Always we
Okay.
put it in the last element, right? That is the definition, right?
That's correct.
Yeah,
So
yeah.
what if I have something on these two position? If I'm inserting anything on these two position, it goes and fits on this path. Okay. So and you could not tell that 35 was inserted or 43 was inserted at the last.
Oh, yeah.
So same goes here. Hope it's clear better now.
Yeah.
Mahi, Pooja.
Yeah, got it.
Okay. Fine. So shall we go to the next question? I mean that's the whole idea about that. See, again. So these kinds of questions you can expect, like these are some tricky questions. All the questions are tricky. Fine. Okay. Yeah, Uma. Not
Yeah.
Uma.
Yeah.
Same. This is also similar way.
This actually I did it. It was on Discourse. I tried it. I traced back
Okay.
of 70,
70,
deleting
61.
95. Then we can.
1 minute. What is this question? Let me just. Should we need to draw this?
Yeah, yeah.
Okay. I did not read the question though. Just looking at the question, I just.
Yeah, yeah. Just explain. They're just saying that this is a max heap. What if the last element inserted was 95? That's all. So how did it look before inserting 95? That's all they're asking.
Oh, before 95, how will it look like?
Yeah.
Yeah.
So you can delete it and try get back that structure with
Okay.
70 as a root node, right? Then we'll
Yeah.
get the answer. Yeah.
So I'm deleting 95. So 70 will go up. All right.
No, last
Wait a
element will
second.
go up, right?
Sorry.
Will it?
It's
Not the
13.
last element will go up. 39 will go up, right?
Yeah.
Okay.
39 will come to that place and then
Yeah.
it'll bubble down.
And yeah.
Oh, okay. This is like deleting the last. I mean, deleting the maximum value in the max heap.
Yeah. Yeah.
Just exactly like that. So
Structure, okay.
ideally, what we will do is we'll put 39. We'll replace 39 with 95. We
And check
interchange
that.
these two positions
Yeah.
and pop the 95 here. Am I right, Srivinay?
Yeah, I mean, that's what the thing is. You can't say when pop 95 is popped, but you can just say that when you exchange it, 95 gets lost. It's not part of the array anymore.
Correct. Okay.
Yeah.
So and we have 39 here, and since it's a max heap, so 39 comes down and 70 goes up, right?
Yeah.
Okay. So right hand side remains the same. It's 24, 47. Okay, let that be there. So 70 is here, and since this is a max heap, right? So yeah, 39 is here. Like we put 70 there and 39 over here, and since 47 is greater, 47 goes up, right? And then the left hand side, it still remains the same, 31. So we had like 39 in this place, and is this 39?
Yeah. Correct.
To the
That
right
is
will
what
be
we have
that.
popped out, right? That is what we have popped out. So 39 will be here. So final list will look like 70, 47, 61. Sorry for the bad handwriting. 43, and we have 39, 24, 47. Do we have 247? Yeah, we have 247. Fine.
Yeah, yeah. In a heap, it's fine. Only in a binary search tree, it's not okay.
12, 31. So let's check with the correct answer. 70, 47, 61, 43, 39, 24, 47, 12, and 31. That's right. Is that clear for others?
Yeah, it's
Mahi,
clear.
Pooja?
Yeah.
Yes.
Great. So just deleting the maximum element in the heap. Nice. We have some good questions in this. Mhm. So, Mahi, would you like to take this question? So, what is this? This for minimum possible weight of path P. Okay. So, path P from vertex 4 to 1. Dijkstra's, huh? We can directly use Dijkstra's, I think. We don't have negative weights. How do you do this, Mahi? Hello?
Someone else can take it. It will be
No, no,
better.
no. No. See, this is an underrated graph and you are given the weighted, right? First, you try to draw the graph. How many
Okay.
nodes are there? Tell me how many nodes are there?
1, 2, 3, 5.
Yeah. So 0, 1, 2, 3, 4, 5. I mean, 3, 4. We have got it. Okay. 0,
Yeah.
1, 2, 3, 4, and 0, 1,
2.
2, 3, 4. Okay, so since this is undirected, the matrix is diagonally symmetric, right?
Yeah. Okay.
You're able to see it, right?
Yeah. Then 0 to 2, it's 8. We have to
Right.
mark it.
Start from 0 to 1.
Okay. 0 to 1, it's 1.
Correct.
0 to
Then
2, it's 8.
mhm.
0 to 3, it's 1. And then it's 4. 0 to 4.
All right. Then
Okay. Uh,
from
1
1 to 2,
to.
you can start from 2. Okay, 1 to 2.
Okay. 1 to 2, it's 12.
Mhm.
1 to 3, it's 4. And 1 to 4, it's 9. Okay.
Apologize for the bad drawing. 1 to 4, it is 9. All right.
Yeah. And then 2 to 3, it's 7.
Okay, no other choice. Mhm.
And 2 to 4, it's 3.
It is 3. And then
And then 3
4
to
to
4, it's 2.
yeah, 2. All right. So we have this. Ideally, I think it's not so confusing.
Yeah.
All right. Just making sure it is good. So fine. So we need to draw the graph accordingly. Then after that, what we are supposed to do, find the minimum possible weight of the path from vertex 4 to 1. Starting from 4, you need to go to 1.
1.
So how do you do that?
So what is 1 to 4? 1 to 4,
1 to 4 or
it's
4 to 1? Draw the shortest path.
9.
Stephen, is this a click?
Sorry, what?
Is this a click? Does this look
9.
like a click? Everything is connected with every other thing, right?
1, 2, 3, 4.
9 actually. 9.
Yeah, if you
Yeah.
look at the matrix itself, you can see that all the values are filled. So yeah.
So for a click, if you want to draw a click of 5 vertices, you can draw it perfectly if you know just the structure. Right? It will come something like this. If you remember, we have studied this in CT. So let me connect this with here. So oh my god, sorry. This is how it should look like. Am I right? Click of 5.
Yeah.
Hmm.
It's 1 to 4. So it's
Yeah.
asking about the weight of 1 to 4. So it's 9 only, na? I
No, no,
guess.
but shortest path can be
Shortest
lesser
path.
than that. No?
Shortest path, yeah.
But there is no shortest path.
If everything is connected to everything, there should be a shortest path, right?
There can be a shortest path, no?
Okay, so then 4 to 3 and 3 to 0 and 0 to 1. It's 2, 1, 1.
4, 4 to 3, 3 to 1.
3 to
So
0,
3 to 0, 0 to 1. So when you're saying the answer is 3.
No,
No, no,
4.
4.
4.
2 plus 1 plus 1.
Yeah, 2 plus 1 plus 1. It is
Yeah.
4. That's correct.
0.
So if you draw the graph, you will get it. But sometimes it's not so visible, right?
Yeah.
It might not be the case. So how do we algorithmically do this? Srinath, we can do that algorithmically, right?
Yeah, yeah,
That is how we are supposed to do in this case.
yeah.
Or we can use the Dijkstra's algorithm, right? Yeah, I mean, so I think there is nothing wrong in this. So should we move ahead, or can everyone do this question,
Yeah,
guys?
got it. We can move ahead. Yeah.
Puja, okay?
Yeah.
90%. Just if you draw the graph, you'll be able to answer that because that's how they will give the question. 90%. Just 10%, it will be tougher. You might need to apply the algorithm. Yeah, go ahead. You only finish this off.
Even I don't know. If all wedges have this edges have the same weight in an undirected graph, which algorithm will find the shortest path between two nodes more efficiently? No idea.
See, all the edges are having the same weight. That's the first one.
Yeah.
Okay. In order to find the shortest path between two nodes, you can use two different algorithms, right?
Yeah.
One is BFS and the Bellman-Ford,
Yes. Yeah.
or same weight, or Dijkstra's also can be used. So, Srivinay, can you answer this, please? What is this
Yeah.
about?
So as you said, I think depth first search will not give us the shortest path. You know that.
Hmm.
So
This is about the
so depth
complexity.
first, huh?
This is about the complexity.
Actually, even depth first search might give us, yeah. If we, I mean, if everything is equal, you can choose to follow the path. But
No, in that case,
um,
depth first will give a longest answer. BFS will go. But what about Dijkstra?
yeah, I
Yeah.
think efficiency wise,
Efficiency wise, I can come up with this here. So, what is the complexity for Dijkstra's? So, this is Bellman-Ford. Where do we have it?
extras with heaps is of n
Oh,
log n, right?
okay. Dijkstra's is n square. Is it so?
Yeah, n square is order complexity without using heaps, right?
Mm-hmm.
With heaps, I think we can make it n log n.
Do we have it here in this or not?
No,
In the
no, I think
future?
it's discussed later, much later.
Mm-hmm. All right.
Yeah, but the
So, the,
bottleneck was that you couldn't always have a sorted list where you have the minimum element. You wanted the delete min, right? That's why we studied heaps.
mhm. What is the complexity for BFS?
Mm, so you're going to visit all the neighbors. So it's going, if you use an adjacency list, it's going to be, if m is the number of
Adjacency list
edges,
we can use. Yeah.
n into m, right? Yeah. So I think that's why it's better.
No, it is
So,
O of m plus n, I believe.
M plus n, yeah. Sorry.
mhm.
So Dijkstra's priority queue is, I think, V log
N
E,
log, yeah, v log, yeah. Vertices log the number of edges.
Okay.
something like that. I'm not very sure, but it is E log V or V log E, something like that.
No, no, V
Uh,
log E, yeah.
V
Because
log E. Yeah.
yeah, the log is on the number. Like you want to have the edges in sorted order, right? So now all the edges in sorted order. So E is the number of edges.
So, but
Mm.
sorting itself will take some time, right?
Yeah, but sorting takes only log n time, right? Log of E time, right?
Mm-hmm.
So when you do the priority queue, which is the heap, um,
Mm-hmm.
if you just create heapify takes uh, v log e, so everything else takes the same time, right? I think every delete takes log of e time, and you do it v times, so v log e there also. So the total complexity is still v log e.
Okay. Seems like n. This is n plus m, right? Ideally,
Yeah, but the m can be maximum n square,
bro.
right? Because
What? Repeat.
yeah, m's m value can be up to n square,
Uh,
right? Because the number of n into n minus one, right?
yeah.
Maximum number of edges.
M is nothing but the number of edges.
Yeah, yeah. And the maximum
Okay.
number
This
of
is,
edges in a graph of n vertices can be
yeah. That's
n
okay.
into n minus 1.
Yeah. That's okay.
That
But
becomes n square. Yeah, I don't
that's okay.
understand.
But so if that is a square, then this also become will go
Yeah,
increase,
but
right?
that is in terms of log. No? So just 2 times log e, right? So in terms of log, if you take log of e square is same as 2 log e, right? So it's a constant. Like you can remove the 2. But in terms of n plus m, if m is at most n square, it's still n
Mm-hmm.
square. It's not going to be log, right?
Yeah.
Not going to be lesser than log.
But see, but the thing is, this is the number of vertices, right? So,
Mhm.
uh, and the number of edges. We have a, you know, the relationship for, if you are having number of edges, I mean, this much number of vertices, then you should have this much number of edges. You cannot have more than that. There is an upper bound for that also.
Yeah, n into n minus 1 by 2, right?
Ah,
Which is n
that's what.
square, right?
Mhm. Okay, let's just take an
Okay,
example.
so just to
Okay.
add to this complexity about the extras, I was just looking into this, PDSA textbook. So it is mentioned that it is m, because the m is coming first actually. M log n is there,
Okay,
so it
okay,
is
okay, okay.
yeah e log v in this case.
Okay, okay. Sorry. Yeah, maybe I got confused.
Yeah, I just pasted the link in
Mm.
the chat also.
Is it so? All right. Let's just look into that.
Yeah, can you open that? Yeah.
Um,
Maybe I missed something over.
To Dijkstra's algorithm using min v.
Yeah, if you go below, you'll be able to see that. So here it is mentioned. Yeah, here it is m log n, no distance updates overall.
Yeah.
So overall it is O of m plus n log n basically, but then
Hmm.
Yeah, m is bigger than n. So
hmm,
So, but in our case, there it is it just m plus n?
yeah. So this is
right,
more less efficient than yeah. You're right.
BFS.
Yeah, it is.
But this log log factor log n factor is not there.
Yeah. Correct. Yeah.
Right.
So
But
yeah.
this we are only able to use because of the fact that all weights are equal.
Yeah, exactly. Otherwise,
Whereas the
breadth first search
extra,
won't. Yeah.
yeah, the extra is more powerful in terms of even if we have different weights, it will still be able to give us the shortest one easily.
Yeah, that's what. So breadth first search it works for equal edges. Then the next level is when there are unequal edges, you can use the extras.
The
If there are
extras,
negative edges, you can use Bellman for, right? It's like
Bellman
a
effort, yeah.
yeah. It's like
And depth first search is like a completely different use case, perhaps.
a,
Yeah.
yeah.
Same weight basically, right?
Hmm.
Or no weight or same weight. Can say like that.
Hmm.
Uma, Mahi, Pooja,
Yeah.
what's your statement? So for priority queue, it is from this we can remember that log n, right? M plus n times log n. So for breadth first search, it is n plus m. DFS we are not considering about it, but for Bellman for is it n square? I don't
Yeah,
remember.
worst case is
Right, n square, right?
I think it's n cube. And I think
Yeah,
it's three for loops, right? Three for
yeah,
loops.
three for loops because we put infinity and then iterate it, right?
Yeah.
So for everything we need to put it. Okay, fine. Okay, good.
So
So,
one question,
yeah,
excuse me. Just one question. In
right.
the matrix that we have, this adjacency matrix, you know, so the in case of directed graphs, so it represents the outgoing edges, no, the rows.
In a
I
matrix, right? Yeah,
yeah,
matrix,
I
the
actually
rows,
outgoing,
yeah, outgoing edges. You're right. And
and the
columns are
y-axis, so to
incoming.
speak, yeah, columns are incoming. Yeah, so I always kind of confuse. That is why I wanted to confirm once again. Okay, it's fine. It's fine.
Yeah.
Say it again, please repeat.
We
So
want
in
me to
case,
repeat? Yeah.
Yeah.
Yeah, repeat it.
yeah,
Okay.
okay, sure.
So this is a undirected graph, right? So it's symmetric along the axis. So we don't have in degrees and out degrees, like in incoming edges and outgoing edges.
I'll put
But
like one like this. 3 9. Go ahead now.
yeah. So in if you want to know if there's a directed graph, just make sure you don't forget that the rows represent outgoing edges, right? So 0 to 2, I think has a edge weight of 1, right? That's what you've written. Third
No,
row,
0 to 2 it is 8,
8.
right?
8 you've written. Is it? Yeah,
0
0 to
to
2 is
2
8.
8.
Yeah, 0
Then we can say that
to
if we have, so this is 1. Okay, so this is 1 and this is 11.
okay, I can't see. Okay, so so there's an incoming edge from 0 to 0. Is it 0 to 2? Sorry, 2 to 0. Sorry, I'm getting confused. So 2 to 0, there's an incoming edge of weight 1.
Yeah.
2 to 0, right?
Okay.
Sorry,
It's the
wait,
other
2
way
to
around. Yeah, it's an incoming edge, right? It's coming into zero. So if you look at the column of zero, it'll
Yeah,
tell
yeah,
you
yeah.
what are the incoming edges. The row of zero gives you the outgoing edges.
Yeah,
Yeah, 2 kilos. Correct, correct.
Yeah.
I'll just go in this way. Fine.
Yeah.
Okay, good. So next question. In DFS traversal of an underrated graph G with n, so E is mod. The number of connected component in G is nice. What is this? Go ahead, Pooja. Try this. Pooja,
Yeah.
Pooja, are you here? Yeah.
Yes, yes. In a depth first travel of an undirected graph G with n vertices, E edges are marked as tree edges. The number of connected components in G is
Okay. So we can take like this. Okay. A, B, C. Okay. Then D, E, F. Consider that you have this is a whole. I mean, this whole thing is a graph. Okay, Pooja,
yeah,
and you're going to do DFS. Okay, if you're going to DFS, depth first search, right? So you will see that all these three belong to a component one, correct?
yeah,
And this belongs to a component two because they are not interconnected. Like you don't have a common graph, a common thing. Okay, so n is the what? N is the number of vertices. What is n?
6.
Right? You have six vertices. Yes or no?
Yeah, yeah.
Okay, how many edges do you have in this graph?
4,
Huh?
4,
Four. Very good. So, what is n minus e? What is the value?
2.
So, what is the two?
Oh, connected component.
Number of components. Okay. So, if by chance you had one more edge, means the number of edges is increased by one. Okay. N minus e is going to become one, and this whole thing is a connected component, right?
Yeah, yeah.
You're connecting them together, right? So, just imagine, like, just let's take another example. A B and then C D. Okay, EF. So if you draw the, similarly, BFS for this. So what is N here? Still 6, right? What is
Yeah,
E in this?
3,
Very good. So what is the number of components?
3.
Very good. Or that which is nothing but 6 minus 3, right?
Yeah, yeah.
If we add
Okay.
one edge extra, number, which means the number of edges 4, and we have two different connected components, right?
Yeah.
Okay. If you add one more, then it's going to become like 5, and the number of connected
Okay.
components is 1. Okay. Hope this is
Yeah,
clear.
yeah, yeah.
Yeah. Uma,
Can anyone tell me why?
go ahead.
So one question here, I think this E is not representing the edge, all the edges that are in the graph, right? Because E, it is saying that it has to be a tree edge in the DFS tree that we get, right? Because in this
Uh,
case, if we were to just add another edge into some, into that same component, perhaps forming a
right.
cycle or something like that, then in that case, you are still increasing the E, but then it is not increasing the number of components, right? So
Okay.
I think we need to take care of the fact that it should be part of the tree edge also, that we get after doing the DFS thing.
Okay. I'm not understanding.
Yeah, I was
Yeah,
about to tell that. No,
yeah,
from
even yeah,
graph, from the graph, we have to take out the DFS tree, then we talk about the E. That's what
Hmm.
I've understood. Even I was
Right,
thinking, yeah.
right.
If P to B, if you have a connection, Gokul, we can't consider this graph. We have to take out the tree. If you draw
Okay.
a
So just mean
vertex,
that,
if you draw edge of C to B, it is a cycle, right?
yeah, which it is not a BFS, right?
It is not a DFS, so we have to draw the DFS first, right?
Okay, for this graph. Okay.
Yeah,
So
that
which
will
means
be
that,
like whatever you have drawn before. It will be A to C, A to B. So
okay.
from that we have to compare, right?
So I can draw a graph like this, right?
Yeah.
So I have A, B, C, D, and then let me have one more thing, E. Right. So this is how it is. Okay. So now for this, I'm
You
going to
can,
start.
okay, you can make cycles. Okay, yeah, you have cycles.
Just a graph, right? So I'm
Yeah.
starting from S. Okay. So I'm going to draw the BFS for this. Is it BFS or DFS? Yeah,
DFS.
DFS.
Excuse me, just to add one thing. So in this case, in the graph that we have drawn, we have only one component, right? So I think it is connected. Everything is connected by anyway. So what DFS will produce will be connected also. So in this graph
Okay.
is like one thing. You can kind of draw a similar thing, that is disconnected also. And then we can perform, DFS tree on both of them. And then perhaps we can talk about this.
Okay. So now I had two different things, right?
Yeah, correct.
Okay. Like okay.
And then we
So we
have to
have
do the BFS. Perhaps in the other component also you can form a cycle just to make it slightly more. Yeah, okay, yeah, that is fine. And then
okay.
we have this other thing. So what should we be getting at the end is two basically, right? Because there are
Uh,
two components, two,
so what is
right?
N? Yeah, two components. That's correct.
Correct,
So what
correct,
is
correct.
N in this case?
So before starting with n, perhaps we can start with the DFS tree thing, no? Traversal and draw
Okay.
the tree, and then we can start with that.
Yeah. Let's say like we are starting from A. Shall we?
Okay, shall we? Okay, it's fine.
So it's a DFS. So I can go to B, right? B to C. I'm just taking alphabetical order, priority. Yeah, is that it? I think that's it, right? We are not connected.
Yeah,
We are
yeah,
not
Yeah.
connected.
yeah.
The
So we
BFS.
have one tree. The other tree is also for the other component that we have. So it will be EFG directly because you can see that it
No,
is
but
easy.
it is not connected, right? So we only have one source node for the BFS, right? No.
Okay, okay. No, I was talking about the other component now because we have one tree now. We'll have to go to the other one also, no?
Yeah.
Yeah, yeah, you do that. So you will start with E, right? E or F or G, however.
Whatever. Let me start with E. Go ahead.
Yeah,
Now
that's
it is over. Now we have how many edges? Two and one, two, three. So we have five edges in the tree, right? So that is E basically. E is five, right? Because the tree edges are five. And now the
Correct.
number of vertices that we have is 1, 2, 3, 4, 5, 6, 7, I think. So we'll have to do what?
Hmm.
7 minus 5. Yeah, yeah, it is correct.
Seven
Okay, okay.
minus five. Now
7
ideally,
minus 5? Yeah, yeah.
okay. So I was
7
also
minus
somewhat similar there, right? 7 minus 5 is 2.
2. Yeah, it is correct because that is actually giving us the number of components that we have, right?
Okay. Okay. Okay.
All right,
So
sure. So
The
that was
total
one
number
point.
of
Yeah, okay.
vertices, total number of vertices. Okay, just how many?
okay. So what is this testing? Like, what property is this testing? Like, there's some overlaying lying concept that's there in this question. Can anyone
which
tell me
Stephen
what
I
it
will
is?
tell? Which Stephen I will tell?
I'll tell you guys if you were if I mean you should be able to find out after you all discussed it and you're able to come to the answer. So you should be able to understand why is this true.
So is it something like a tree will always have n minus one? So n is basically the number of
Exactly.
vertices, and the
Exactly.
n minus one is
So
the number of.
any tree with n vertices will have exactly n minus one edges because it cannot have lesser than n minus one. It cannot have more than n minus one. Right? If it has more than n minus one, it will form a circle. And if it has less than n minus one, then it cannot connect all the components. It needs at least n minus one edges to connect the components.
Yeah, that's a nice point. Right. Guys, did you guys understand what Shivani was telling? Uma?
Yeah.
Okay. Pooja Mahi, any doubts? Like if you didn't understand the previous statement, you can ask.
No, no, it's clear.
Right. Okay. I think this one is also clear, right? Only thing I think
So
I forgot to go ahead, Afrin.
yeah, so just to add to this n minus 1 thing, what I am able to see here, perhaps intuitively, is that EFG you have two edges there, no? So that is 2, and then in the other one you have 1, 2, 3. So that gives us a 5. Now assuming that we connect, right? So we connect these two, right? From A to E, perhaps we draw an edge, then that will give us 6, which is exactly equal to n minus 1, right? I mean, we have 7 minus 1, which is 6. So that is giving us, no, in the tree that we
Yes.
have drawn, talking about
Correct.
this one, right? So that gives us a fully connected thing, right?
Yeah.
So the fact that this one was missing, I mean, this particular thing was missing E to A, that's something that we only added now. So that is that is actually giving us the number of components now because individually they form a tree, but they are not connected, right? So n minus 1 from there and n minus 1 from the other one basically is
Correct.
giving us that 2. Is that right, Shrivana?
Yeah. Shivane, you say.
N minus one from the other one. Okay, I'm not able to understand that.
Okay,
Ah,
So you're
okay.
saying, oh,
I was
N.
talking about the
Okay.
tree actually.
Mm-hmm.
So the tree, you have EFG and you have 2 there. So that is also n minus 1, no? If you talk
Yeah,
about
yeah.
only that. Yeah.
Correct.
And the other one, you have what you have? A, B, C, D. So you have
Four
3 there.
minus three.
4 minus 1. So that is 3. And then overall, you have 5. So basically, you have one missing because if you had that one, you would have connected
True.
those two components. Right.
Exactly. Exactly.
So the fact that we have 2 n minus 1, n minus 1, but overall, you have one missing, that is giving us the number of components, right? I mean, mathematically.
Yes,
Yeah, yeah.
yes.
Okay, correct, correct. Thank you.
Great. Fine. We'll go to the next question. Fine, fine, fine. Okay. Who's gonna do this question? Afran, you have to do this question.
Yeah, I
All right.
think he was just
This,
asking
I
about this
think, yeah,
question.
this question we just discussed is the same thing. We may,
Huh?
we may, yeah, I can do that.
What do you mean? What do you mean? I don't
So no,
understand what.
I was asking about this matrix thing, no, which columns represent the incoming thing and the rows represent the outgoing edges.
Ah,
So
okay,
this is
okay.
yeah regarding the same thing. So it is saying that ij a mat of ij is equal to 1. That gives us the fact that it is a unit weight. So in case of unit weight, if we sum, then what we will get is the out degree, right? If we sum the rows, then what we are getting is the out degree because everything everything has just one weight. So if we sum, then that will essentially represent the count, which will give us the out degree. If you are talking about the row, right? So that first option is correct. So the sum of row of I represents the out degree of vertex I. Whatever vertex you put in there, if you sum that, you'll get the total number of edges that are going out from that vertex I. All right.
Correct.
And similarly for columns, if you go to columns, then vertex assuming vertex j or whatever. So then vertex j, if you sum that, then you will get the incoming, right? So whatever is incoming into that vertex j, you will get the count of that, and that only is because of the fact that ij is given as one. Had it been something else, then that would not be true, right? Because summing, then it will sum the weights, but in this case we have one only, so that is giving us the count. So that is the thing we need to also keep in mind, that because it is one, then only we are able to count that. Otherwise, we will
Yeah,
have to
yeah.
use something else. Yeah. Yeah.
Correct.
Then perhaps in the other case, perhaps we can do this non-zero thing, right? Whatever is non-zero, that will give us the count perhaps. uh,
Yeah,
or
Yeah.
that's also right. Yeah.
no, in the case of weighted matrix, if it is non-zero, then whether
Yeah,
it be
yeah, you're right.
yeah, yeah. So in that
The
case, I
non-zero
think
is negative or positive is also fine, right? Non-zero is, yeah.
yeah, perhaps none, no, none also we can. Or in the
Mm.
case of Bellman Ford, we have infinity and things like that. Something that represents non-reachability, right? Non-reachability. So if it is not
Mm-hmm.
there, then we cannot reach from there. So it is like none. So anyway,
If
so
this
summing
question
that
was
will give us the out degree and in degree. That is all there is to it. This question. Yeah.
Yes. I hope
okay.
everyone else understood. I think it
Yeah,
was
that was
pretty straightforward, right?
yes.
Yeah, got it. Yeah.
Okay.
So in binary classification, if you have to find out this is from machine learning actually. So if you have to find the number of samples representing class one, that is so easy, right? Because the other class is zero only. So you sum it up
Yeah.
and you get the number of
The count of,
samples in
yeah.
the class one, right?
Yeah.
So the same thing.
Fine. Go ahead. This question. True with respect to merge sort and heat sort. Yes. Did we learn about heat sort, guys?
No, we didn't see, but yeah, we have. I just finished it. Yeah.
Okay. I don't know what is this heat sort. Have we been taught in this?
Yeah, yeah,
Yeah.
we have actually. I think PP5, right? That's kind of closer heat source.
Yeah, yeah. So you just use a heap, max
Yeah.
heap or min heap, to be able to create a sorted list. So that's,
Oh, okay. Is that the case? Okay, okay. I didn't know that. We didn't have a separate lecture on this, right? Something heat sort. Did we
It
have?
was not separate, but it was part of one of the lectures, which is like implementations of heaps, like heaps, right?
Okay,
I
okay,
think
fine.
it's like that. Yeah.
So what's this? Which of the following is true with respect to merge and heap sort? Was Kate complexity of heap sort the same as the merge sort?
Does someone want to take this? Do you guys remember heap sort? Right. Okay. You want me to explain heap sort maybe?
Yeah.
Yeah.
Yeah. Okay. So, so what does a heap do, right? You have a max heap. If you have a max heap,
Should I do a max heap?
uh, yeah, any max heap will do.
I have some random numbers. All right.
Yeah. Yeah.
Should I make this as a max heap? I should make it as a max heap, huh?
Yeah.
All right. So 2 1 because I know 1 2 it is going to change. So then
Hmm.
I have 4 over here. Now 4 goes up, which means 4 2 1. Right. So oh my god, I had taken this in the wrong way. All right. It's still fine. Let's do this. I have 3 here, which means 3 will go up and 1 will come down. Hey, just ignore this. Like I'm just gonna try. I'm just trying to form a heap.
Yeah. Yeah. Oh,
So and I'm inserting 8 here, which means 8 will go up. 8, and then comes 4, then comes 3, and then comes 1. There goes 2. Right. Next I have 5. Okay, 5 will go here. 2 will come here. Then I have 6. 6 will go here. 5 will come here. Okay. Now I can write the maxi pass 8 4 6 1 3 2 5. Yeah. Go ahead. Do the
yeah.
maxi.
So, in a max heap, you have the maximum element on top, and whenever you make the max delete, you know that it restructures itself so that the maximum is again on top, right?
Yeah.
So if you keep if you're taking a max heap, all you can do is keep popping the last element, like the max element,
Hmm?
and put it into a list, right? Insert it into
Okay.
a list every time, right?
Okay.
So first you will
So
insert 8, right?
yeah, insert 8, and then insert like again pop the
Somehow
maximum
it
one.
restructures. Yeah,
Okay.
yeah. You don't have to know the entire process. You can just think of max heap as a function that always returns the maximum element
Maximum
in the
value at the
entire
top.
list, right? Yeah.
Correct.
So
All
you're
right.
able to get the entire, yeah.
4 3 2 1. Something like
Yeah.
this. So we are adding it in the front basically,
Yeah,
right?
inserting it. Or if you take a min heap, you can do the opposite. You can just keep appending it there.
That's right. Okay. So what's the point over here? I think this is going to be like taking a big of n step, right?
So you're doing
Adding
it for every element. For every element, you're doing delete, right? And the delete complexity of delete is log n. Every time you delete, to restructure the heap takes log n, right?
yeah,
So you're
restructuring
doing
takes log
it, yeah, yeah. So n log n. That's the complexity of,
n log n. That's very interesting. Okay.
yeah.
For the merge merge sort also is the same, right?
Yeah, it's the
N log
same,
n.
yeah.
Is it n log n or n square?
No, n log n squared in the worst case,
There
right?
are two algorithms with the n log n. One is the merge sort and the quick sort.
One second. Merge
Not
sort.
everything is same, n log n. Worst case and the best case.
Yeah, yeah.
So, okay. Okay.
You're right.
So
You're right.
quick sort works. Worst case is n square. The
Yeah.
average case is n
Yeah,
log n.
yeah. Exactly.
So why is quick sort quicker than the merge sort sometimes? Why?
Are you asking me, or like
I'm asking.
do you want to know the answer, or do you want others to answer?
I don't know. That's why I'm asking. I
Oh,
remember
okay,
quick
okay.
sort quick
If someone
than
wants to answer it, you can answer it. Do you guys know why? Why quicksort is preferred?
hmm.
So we know about
Is
merge
it, is
sort
it because
being
in
Space
place?
complexity.
For space,
Yeah.
yeah. Yeah.
yeah,
It's,
exactly. So merge sort takes a lot of space,
yeah.
right? And the merging step, say in quicksort, you're able to do it in place, right? That is one big advantage. But
Correct.
even so, the problem is, see, we know that when we have a when we're trying to do complexity and phase complexity, we care about time complexity more. So even though merge sort is n log n, we prefer quicksort because the average case happens most of the time, right?
Yeah.
Hmm.
And
The
Worst
average
case
case
is the two
happens,
cases, I think, right? Worst case is just the two.
yeah, two cases,
I
but
think.
it depends upon, see, the whole worst case scenario depends on how you're picking the pivot, right?
Ah, yeah, that's right.
So if you're picking the first element as pivot every time, and if you're given a ascending order list, that's the worst case for you. Same
Yeah,
thing if you're given a you're picking the say let's say you're picking the
last
every
element.
second element, yeah, every time you're picking the second element as pivot, right? And in that sense, if you have the second element being the smallest every time you split it into half, that's also a problem. Like it's not, there's always a worst case, right? It doesn't depend, there's always a worst case, but it's different for different pivot pickings, right?
Correct, correct. Got it.
Right. But in the average case, we know that if there are n elements, like the probability of picking any element, you can either you can do something like random, right? Pick any random element from as a pivot. On random, if you keep doing it, you'll always have the uh, you know
Average fee.
between 3/10 and 7/10. I think you have this 3/10 7/10 somewhere else also, right? Do you guys remember? I think median of
Median of
medians. You
median.
guys remember?
Yeah.
Yeah.
That's
Just
okay.
like that. Yeah.
Fine. Good. And
And quicksort with median of medians are always better, right? You can always make it better.
that's right. That's right. Oh, that's the okay. That's fine. Fine. So,
So
what is
one,
this
so
point
one
about?
question, if I may ask,
Yeah.
this merge sort, it is a stable as far as I'm able to recall, whereas quick sort is not,
Yeah.
Hmm.
right?
It shuffles 1 second. Let's see pivot. It moves. No, if you're going from left to right, shouldn't it be stable? Let me just check a second. Give me a second. I think it should be stable. I mean,
Yeah,
just
that's correct.
imagining it,
Merge is
it's
stable. Merge is stable, right? That's what you're saying.
Merge is stable, that's for sure. But then quick sort, I'm not very sure of that.
Not stable. It's not stable
okay. It is unstable. Yeah, it's unstable
because
because
you
you are
interchange the
swapping.
values.
Yeah. You're
Pivots
right. You're right. Yeah. You
when there
move
is
the
an
pivot
interchange.
to the
Yeah,
Right.
center, and then you. Yeah.
So
that's the
then if
problem.
we have a condition that we need to have stable, then perhaps we'll have to go to much sort, time
Yeah.
complexity is the same. We'll have to kind of give more space and get that stability kind of thing.
Exactly. We
True.
have to
True.
satisfy the constraint. Right.
I think one of the examples the professor talked about was when you want to work with disks, right? Different disks. So when you work in the RAM, right, you can only take a little bit of information every time. So merge sort is better in that case, right? You can take smaller parts of information, work on it, and then merge it up later, right? But
Like in
quicksort, you have to
streaming.
take the entire list, and then you have to like,
Yeah.
yeah,
Yeah. In streaming, we usually do that, no?
exactly, exactly,
Large videos and all those things. So we
yeah,
kind of work on the small part and kind of keep going on.
true. Divide and
All right.
conquer, right? Yeah. And
Done.
even quicksort is, but you're doing it in place, yeah,
Yeah. All right, guys. Done.
yeah. You can go.
All right. So sort is better than the merge sort. No, this is not the case, right? Second option is wrong. We just saw. Okay. So heap sort less space than merge sort. Uh, why does merge sort take more space than heap? Why?
So same thing, no? Another list we are creating, no? That is called the C list in the merge function, if you remember.
Okay,
No?
we'll have
That is,
two lists.
yeah,
Then
that is giving us the final thing, right? When we are merging, in fact,
okay.
so many more lists we are creating. No?
Yeah. Okay. So in terms of quick sort, we'll just So we
We take
create more lists basically, right? In terms of heap sort. So merge sort.
merge sort, yeah. But in the case of heap sort, I think it is behaving as it is, like in place, right? Because we are only working with the heap. There is no other thing that we are kind of allocating into the memory.
Basically, data structure comes into the picture, right? Dot left and
Exactly,
dot right.
exactly.
Yeah, Uma, you wanted to say something.
No, I'm just about to say in the array itself we are swapping, so there is no special space needed for heap
Correct.
sort.
So heap sort is stable sorting technique, but merge sort is not. Is it so? Is it so? I don't know.
I don't know about heap sort, but merge sort is stable, right? That is we know.
Yeah.
Half the thing
Merge
we know. The front part I don't know, but at least this we know, so it is false.
the heap sort stable. Okay. So what if we have does heap allow duplicates?
No,
What
no,
if
it's not stable, right? Because it's similar to quicksort. It's just so what actually they do to complete heap sort, right? They don't work with the data structure. What they do, see, you have 8, 4, 6, 1, 3, 2, 5, right?
so Steven,
So they
Steven,
know, yeah.
please, I have a question here. So we have
Mm-hmm.
eight. Okay, this is the list. Okay, if I'm popping eight, okay,
Mm-hmm.
eight goes here. Which of the eight comes up?
Yeah, you might need a break-even function, right? You just need
Yeah,
to pick the right or left. Yeah, yeah.
correct. So we
You
don't
can
know
say
which
every time I'll pick the right. Yeah, every time I'll pick the right.
eight
Every
is
time I'll
not
pick the left.
complete
Something
stable.
like
We
that.
don't know, right?
Yeah, yeah,
And if you are making sure, I mean, keeping in the memory that okay, this is the order that we are storing, then that's going to take
mm-hmm.
more memory,
Yeah, yeah.
right? Order also make. Okay, go ahead. You were saying something. I'm sorry to interrupt.
Sorry, can you hear me? I just
You
got
were
a
saying
call.
something. No, you were
Yeah, yeah,
saying something.
yeah. Again, just like quicksort, right? Heapsort also they work with the same list. So what they do, they know 8 is the maximum, right? So they move it
Hmm.
to the last of the list,
Hmm.
right? And then they say that the length of the heap is just n minus 1, like len of n minus 1, right? So the
Hmm.
what they do is they reduce the size of the heap. It's like they delete that, like
Correct, correct.
delete, right? Yeah, they put it in the last and they work with 4, 6, 1, 3, 2, 5. They restructure it. The 6 comes on top, and again they keep doing that. They keep putting it in the last.
Okay,
Yeah.
fine.
So that will give you the sorted, like 8, 6, 5, 4, 3, 2, 1.
Yes,
However we should do. Yeah. So in place, but it's unstable.
unstable. That was good. Okay, one last question, and we are finalizing. So I thought, like, okay, who wanna finish it off? Finish this off, Mahi. Just read the question. Just read the question. We'll talk.
Consider the following algorithm on a connected weighted graph with n vertices and m edges. Sort the edges as E1, E2 up to Em in decreasing order of weight.
Okay.
Consider, consider each edge Ei in a sorted order. Okay, if the edge is a part of a cycle, then delete it. Otherwise, keep it in the resulting graph. Okay, the following statement is that
What
true.
is this algorithm? Before we read the options, what is this algorithm?
So and decreasing order. Is this any algorithm?
Oh,
Crystal.
decreasing. Okay, okay.
Yeah. If it was
I thought it
increasing,
should
it
be
will tell us
increasing order.
Kruskal.
Then okay.
Okay, okay.
It was Kruskal, right? If it is increasing order.
Yeah, yeah. If it was
Yeah.
increasing order, yeah, it's good. Sorry, sorry. I didn't see the increasing.
Yeah. So this is decreasing. So this is gonna give us the maximum cost spanning tree, ideally.
Yeah.
But still, it'll be called MCST, because
MM. That was interesting. Yeah. Okay. So my like, did you understand what we are talking? MCST or something?
Yeah,
Okay.
we have to find the maximum cost spanning tree.
Okay. So what is it
No,
saying? What is it saying?
exactly. M minus n plus 1 edges will be deleted.
Is that true?
Okay, I don't know.
You don't know.
Remember the property of a tree of an acyclic graph, right? Again, the same thing.
Okay.
If there are no cycles, there are n vertices, and there are no cycles at all, and all n edges are all n vertices are connected. How many edges do we have?
N minus 1, right?
Yeah, exactly. So if you need n minus 1 edges completely, so you have, how many do you have to delete? If you have m, you want to get it to n minus 1, how many do you have to delete?
So you're saying if we have m and we have some minus x equal to n minus 1. Is that what you're saying? And we want to find out what is x, right? How many edges we are going to delete it.
Yeah.
So n comes less equal to x. Is this correct? Oh my god, I'm good at algebra.
Yeah.
I'm good at algebra. So do you guys understand what is happening?
No.
Just
You
until
keep deleting until you have n minus 1 edges. So that's what he's written. You have m. How many will you delete? You delete until it is equal to n minus 1 edges, right?
Okay. Okay.
So then you just rearrange.
But
Okay.
so, and we know that if you keep on deleting the edges which are trying to form a cycle, then it will end up with a tree, right? Mahi, did you follow
Yeah.
what I said?
Yeah.
Okay, so that's what we are trying to form a tree, and we know that tree will have n minus 1 edges, right? So if you want n minus 1 edges, how many edges you want to delete? That's what they are saying. Exactly how many edges are will be deleted. Got the point? How it is getting deleted?
Yeah.
Good. That is exact. That should be exact, not at least or at most. Okay, to form a tree. Fine. So that's what this option is wrong. So after processing all m edges, the resulting graph is connected. Is it true? How do we see that?
no, we have
You
deleted.
started with you started with a connected weighted graph, right? So all edges are all vertices are already connected.
It's okay.
And
It's saying that it's connected here, right?
yeah.
That it is.
So you're only removing the ones that make a cycle, right? If they don't make a cycle, that means they're connecting something new.
Yeah. Mahi?
This equation that we have wrote, sorry to interrupt. So one question.
Go
So
ahead.
this equation we have wrote m minus x is equal to n minus 1s. So the target we set it as n minus 1. That is also because of the fact that we need to remain connected, right? So this assumption
Yeah.
was also going on there also, right? Why do
True,
we
true.
keep it as n minus 1 is because of the fact that we need to be connected. That is what. Right. And given the fact that we are kind of targeting for n minus 1, that itself is kind of assuring that we'll get a connected graph in the end when the
Yes,
algorithm finishes.
correct.
Yeah, because it does not allow cycles. Because there could be
Correct.
n minus 1 edges and cycles, but then you couldn't have had a connected graph, right?
Hmm. Correct.
Hmm.
Yeah.
That's a good point. Mahi, okay with that?
Can you repeat that point?
Yeah.
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 Fine.
Maybe do you want to repeat
Okay.
it?
Yeah.
Yeah. So the last point was, so we can have n minus 1 what edges. Okay, and this could have been like if you had disconnected graph, then this x plus 1. So if you remember, we had three things. I mean two graph. This was having four. I mean four vertices. This was having three vertices, and how many edges do we have in here? So this should not be a cycle, right? Sorry, someone else tell.
Okay, okay. I thought the other student, I'm sorry, I forgot his name, Afnan, right? Yeah, I thought he wanted to explain. Anyways,
Oh no,
um,
no, you can take it. You can take it. Okay.
yeah, sure, sure. So, see, n minus 1 edges alone, if I'm saying I have a graph and there are n minus 1 edges, I'll ask you a question right now. There's a graph and there are exactly n minus 1 edges. Can you tell me that this graph is definitely connected?
Uh,
Well, yeah, you can answer that. Yeah, okay.
Yeah, yeah, Mahi, I wanted her to answer. Yeah,
it's connected. It's fully connected, I guess.
yeah, it's
And
fully connected. Is it?
yeah.
So think about this. Is it fully connected? It's You're saying it is, right? I'll give you a counter example to that. Say I have three vertices. No, let's take four vertices, right? And
Go
I'm
ahead.
connecting only three of them with three edges, right? I need four. I have four vertices, which is my n. N is equal to four, but I have three edges, right? I told you I have three edges in the graph. What if I'm only connecting three vertices, right? I can create a cycle. So the important part is there should not be any cycle. Then only the n minus one edges makes the tree a
Cool.
connected graph, right?
Yeah.
Yeah. So that's one point. So that's why in the question when they've said if it creates a cycle, then delete it, right? That means
Okay.
you're removing the ones only if they remove the cycle. If they don't remove cycle, that means they're connecting something new.
Okay, okay.
Yeah, yeah.
Got it.
Srivinay, so in that graph drawn, after
Mhm.
processing all the edges, we have deleted the edge. The resulting graph is connected. Okay, that tree is connected. That is what we're talking about.
Yeah, initially the entire tree was the graph was connected, right?
Yeah.
All the vertices were reachable, right? From any vertex, you were able to reach any vertex. But initially there were cycles. There were cycles, right? Because there are m edges and there are n vertices. Imagining m is greater than n minus one,
Yeah,
right?
but still three is not connected, right? So it is
Yeah,
not.
three is connecting. No, no. He only put two. Two is not n minus one. Like n is four,
Yeah.
n minus one is three. So he has to put the third, right? Okay, you start with yeah, connect everything once. Let's just make a small demo of this
No, no,
code,
Srini. I
right?
want without
Yeah.
connecting, disconnected one.
No, no, that's what. We are not starting with a disconnected one. We are starting with a fully connected graph, right? In this algorithm, or do you want something else? Do you want me to explain
If we
something else?
connect, okay, okay. No, no, I was thinking if the example is like, okay, okay. So in
Yeah.
this example, everything is connected, right?
Yeah. In the example, everything is connected. And then we're removing those which are creating a cycle.
Yeah, that is fine. I thought when you talk about disconnected components, I was confused.
Ah, okay,
Okay.
okay.
Fine. Good discussion.
I
Fine.
think there are four more options. Oh, yeah.
Yeah, we saw the third option, right? We saw that it is going to be connected, right? My remaining also you two you have. Yeah.
What remains at the end is a minimum cost spanning tree.
Ah, is it so?
Yeah, it cannot be possible, right?
Yeah, I don't think so.
Is it?
Mm, yeah,
So
it cannot be a minimum cost vanity. It has to be a maximum cost vanity.
whatever.
Mhm.
And this is okay, right? After processing
Yeah, the
all
last
images.
one is yeah, the last one is just the same. So they're saying they
Why
sort the edges as E1, E2 until EM in decreasing order of weight. So E1 is the highest, right?
correct?
Yeah, I don't. Yeah, it should be a max. It can't be a minimum. I don't know about maximum, but it can't be a minimum.
Fine. There is this some wrong in the first question paper, something like that.
Yeah, maybe. Yeah, maybe this is because we can clearly see it should not be minimum. Yeah.
Yeah,
So the second point, they are saying that consider each edge,
exactly.
EJ in sorted order.
That's what
What
I
does
was
it
connecting.
imply? Yeah, what does it imply? I mean, they saying
Yeah.
that we need to again consider ascending. But see, even if we assume that, what I'm thinking is that even if we assume that okay, we have the list sorted in the decreasing order, and then we start picking things in the ascending order, just to kind of assume that. But then the fact that we are initially taking the maximum one, we may left out on some paths which had lesser, cost, and then we did not include it in the list at all. So even if we do the ascending one, that will not give us the absolute minimum cost, right? I hope my point.
I didn't get the last point.
Yeah,
So my
see,
okay,
tell you finish first.
okay. So no, I was saying that they are saying that we are picking out the weights in the decreasing order, right? So from the original graph. Okay, and then we have a list there, and then assuming that the second point says that we have to pick them in the ascending order, then also we'll not have the minimum cost spanning tree is what I'm saying,
Why not?
right? It is because we may have something which is minimum, but then given the fact that we are only choosing the maximum one, we may miss out on something which was smaller, but we did not pick it in the first place, right? In the first point itself. So the
No,
list
no.
does not have.
No, I thought you said okay. So considering okay, let's say E1, E2, E2, E3 all the way to EM is in the descending. It's in descending order, right? When
Correct.
they're saying second point, the only way the second point is true is that they're picking the last element from the last and they're picking it in
Yeah,
reverse, right? That's
correct,
that's
correct,
right.
correct.
If they pick it in last and come back in reverse, it will give us the minimum cost spanning tree. I don't
So
know why
yeah,
it
okay,
shouldn't.
it may be, but my point was that in that case also it may not give the minimum cost spanning tree. Is what I'm trying to say actually.
Yeah, that's what I don't understand why, because I'm sure
Yeah,
it will, right?
yeah. So no, my thinking is that since we are initially picking the highest weights, then we might miss out on something which was less, but we did not pick it because of the fact that something connecting A to B, and A to B there is this other path, right? But
Hmm.
we took out the maximum one from that. So in the list that we got, it might be the lowest, but then in the original graph there was something else which we did not pick in the original list itself, right? So then how can we say about the graph that we got a minimum cost spanning tree, right? I mean,
Oh my God. Okay, okay. I think this is actually right. Okay, so no, 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 no. Yeah. When you said this, I think I had the realization. See, it is in decreasing order of weight. You're right, right? And I'm taking the biggest one first, and I'm saying, should I delete it or not? Now, when will the biggest one be in the graph? So right now the entire graph is connected, right? If I'm picking, okay, hey, can you make a graph so that we can work this out? Can you make a graph with 5 vertices and have weights 1, 2, 3, 4, 5, 6, 7, 8? How many? 5 into, so 5 into 4, 20 edges. No, I don't want 20 edges. Maybe
Oh,
just like 10 edges. Yeah.
One point to just my doubt. See, it
Mhm.
says decreasing order we have to sort the edges, but doesn't say we have to pick the maximum one, right? We can
yeah.
pick from minimum, right?
No, I'm saying even if you pick it from the maximum, you're going to see. Okay. Can you just connect? I'll just quickly do it as a visual. Maybe confirm myself also that I've understood it, and then I'll try to explain if I'm going in the right path. So can you just give distinct? Just give it in tens, no, so that I can distinguish between the vertices and the uh, yeah.
Do they have any common?
Yeah, yeah, 60, 70. Yeah, this is perfect. So what will we start with? We'll start with 80. We can
Wait
see
a minute.
that.
Let me see. Sort the edges E1 to EM, whatever, right? In the descending order.
Yeah,
So let's say like yeah, we have like 80, 70, blah blah blah.
yeah, yeah, we already have that. Yeah. So what
Okay,
he's saying is we have a connected graph now, right? We're able
correct.
to reach one through two and going from three to two, two to one. We're able to go from three to four, four to one, right? That means the edge 3, 1 is forming a cycle. I can
Yeah, yeah.
safely remove it. I can safely remove it, saying I can still reach one even if I remove this edge, right?
Hmm.
So in this sense, if you keep recursively doing it, you will end up
Yeah,
with
then we'll end up with a
minimum cost.
spanning tree.
Yeah,
That's
yeah.
right.
So I'll
So then
remove this. Then I'll remove 1 and
70 is still
70.
forming a cycle, right? 1, 2, 3, 4.
Yeah, yeah.
I'm removing that. Okay. Then 60 is also forming cycle with this. I now I can imagine.
Yeah,
Okay.
yeah, exactly.
So now that has to be 50. We can't do that. So then
Exactly.
50 we cannot delete it. So then 40, right? Seems like I cannot delete 30. Right? Ideally we had one edge. These two
Hmm.
edges I did not give any value. I'll delete them.
No, no, you have to remove 20, not the 10,
Okay.
right?
So
You
it
have to
is.
remove.
I did not give a value for this edge.
Oh, okay. Let's say that was
Forgot.
90, it's fine.
Seems like that was not there. Right. So now this is okay. I think there is no. This is MCST.
Yeah.
Okay, that was a good discussion. Nice discussion, guys.
I think I lost a lot of people when I was doing this. Do you guys understand this one?
Yeah, yeah.
See,
So
there's no
even though it
key.
is in descending order, it's also gives a minimum cost spanning.
Yeah, yeah.
Because in the cycle deleting, we can remove the higher order. That's what it is.
Exactly, exactly. Yeah.
So
Okay.
this
so
point, if
Best
this edge,
example is take just 3 vertices and give it a cycle. You will see that picking the two minimum and removing the maximum one is the same, right?
But one question, Sri Vinay, like
Yeah.
because of sorted order and decreasing, we will go through the higher order, right? We will here we did it randomly choosing 80, but in our process in the question, we'll pick 80 and we might choose delete the 31 because it is forming a cycle. Will it not happen?
see consider each edge ej in sorted. So if this is the, like they are literally playing not with our pdsa, they are literally playing with the words.
Okay, so if the 80 forms a cycle, we remove the 80 even in the first place, right?
Exactly. Yeah,
Exactly. Yeah.
Okay, yeah, got
this is more about english 1 and 2.
it. Very tough English.
Myself, I did not even study that. Fine.
The way to, yeah, the best way to rephrase the question, if I were to set the question paper, I would say, I mean, I think this is a good way to make them think, is that if I remove the edge, if I remove this current edge which I'm looking at, which is the highest right now, if I remove it, am I still able to go to that vertex, or is it getting disconnected? That's all.
That's good. Okay.
Yeah.
So in the case of Kruskal's, what we do is in the ascending order, we pick the elements and we add
Yeah.
those, right? So in this case, we are deleting, whereas in the other case, we are inserting. So
Hmm.
because we are taking it in the ascending order, we kind of keeping it, right? So we start with the
Yeah.
lowest, keep it there, and the next lowest, so on and so forth. And at any point in time, if we get a cycle, then we'll not include that. Whereas in
Yep.
this case, we are kind of doing the invert of that process, right? So we have the graph, but when we are starting from the maximum and deleting that, if it is forming a cycle. If it is not
Yeah.
forming a cycle, then we're kind of ignoring that, right? So this keep it in the resulting graph is more of ignoring that because it is already there, no? I was thinking that it is like inserting, but we are not inserting, right? This is statement, keep it in the resulting graph. What it is
Yeah.
like,
Yeah. Keeping. Yeah.
yeah. So it is like it is already there. No, we are not inserting.
Yeah. It's
Yes.
already there.
Hmm.
The previous
Oh,
ones you deleted because you were able to reach that vertex through this, right?
hmm.
Because
Because
it
you
was
only.
connected.
Hmm.
Yeah.
Okay, okay, I understood now clearly. So what happens is that Kruskal, you pick out the ascending, ascending thing. They go by the minimum ones, and finally, what is left out? If you think about this, what is left out is only the higher order weights, which were forming a cycle in the original algorithm. That is what happens. So
Exactly.
what we are doing is we are removing those initially itself, right? So it is like the invert of that process.
Hmm.
Yeah, like you said, you should understand English more than the question
Yeah,
Exactly.
because this is
yeah.
crucial. If this edge is so, from the starting itself, we have to consider in deleting. That was my doubt. Okay.
Hmm.
Fine.
It's
Okay.
clear now. Thank
So
you. Thanks so much.
yeah, yeah. That's super good. Okay,
Thanks,
Mahi.
Keith. I
Okay.
think tomorrow you're not having sessions, right?
No, no, that's all. The sessions are done.
If there's something you guys want to discuss, just